Okay, today we'll be looking at different types of Eurocode actions and how to model them inside a numerical analysis software and how to consider them in the finite element analysis and design of a bridge. The types of Eurocode actions we'll look at self-weight, permanent actions, wind loads, thermal actions, earth pressure on abutments, and the relevant codes are all listed next to the bullet points. Traffic loads, footbridge dynamic analysis, load models, accidental actions, and then finally we'll sum up the presentation by looking at the combinations of actions for bridges. So starting with the types of Eurocode actions, Eurocode defines the following types of actions to be considered for bridge design. We have permanent actions, which includes the self-weight of bridge and other structural components, weight of earth, etc. Variable actions such as traffic loads, wind loads, thermal loads, accidental actions such as impact loads from vehicle collisions or scar below foundations, fire or overloading of the bridge, and seismic action including earthquakes. So today we'll be looking at mainly the first three types of actions: permanent, variable, and accidental actions. Starting with the permanent actions, these are the different types of actions that Eurocode suggests to be considered as a permanent load, which includes self-weight of structural and non-structural components. Now Eurocode 1 has given us some guidelines for the weight density to be considered for different materials. So I've just listed out few of them, which are most commonly used. Weight of bridge furniture, which includes parapets, surfacing, ballast for railway bridges. Weight of earth, which includes vertical pressure due to overburden on culverts, so very common for box culverts and other types of buried structures. Now these permanent actions can be included in the numerical analysis in a variety of ways. So if it's self-weight, the numerical software has auto self-weight loading option. Parapet loading, you can apply it as a line beam or a UDL, element beam loads. Surfacing can be applied as a floor loads or pressure loads, and weight of the earth can be applied as a pressure load. So let's briefly look at how to apply these loads in the software itself. That's the Midas civil modeling interface. So I'll just quickly show you how to apply different types of loads, permanent loads. So you go to the loads menu and you have self-weight option. First of all, I defined some load case names here, just a few names to be assigned with different values. Self-weight is assigned with a factor of -1 in the z direction. So automatically wherever you have considered densities, software will apply self-weight in the gravity direction. Then element beam loads, which are generally the parapet loads, for example. You can change the load case name to parapets. Select the beams which represent the parapet beams and apply some loads on them. So I'm selecting some of the beams here, enter some values, say 10 kilonewton per meter, and direction global Z, vertical direction, and parapet load will be applied on the structure. Then surfacing. So surfacing can also be applied as a UDL on the main girders. So we are looking at a composite girder bridge. If I change the view here, this is a composite steel girder bridge. So surfacing can be assumed to be conservatively applied on the main girders itself. So just like a line beam load, they can be applied as a uniformly distributed load on top of the main girders. Now there is another approach for grillage models for surfacing. We can assume a two-way type of distribution on top of the grillage model itself, grillage deck, and distribute it on the longitudinal as well as on the transverse beams. So let us see how to do that. So I'll just activate the deck itself. Isolate the deck. So that's the deck. Isolate it. And then define the floor load option. So I have two types of floor loads here, surfacing and footway construction loads to be applied on the footway. So I've defined some values for it. So footway is, for example, 4.8 kilonewton per meter square, and that's 4.63 kilonewton per meter square. and then I will assign the area on which the surfacing load has to be applied. So it need not be that the entire deck needs to be loaded. We can select the area for, say, covered by the intermediate beams. So say surfacing distribution type is two-way, and I'll select the nodes which represent the surfacing area, so something like this, and click apply. So now you will see, if I zoom in, you have a two-way type of distribution on the longitudinal and the transverse elements. Similar things can be done for footway construction, and we can assume an actual distribution on the slab itself. So going back to the presentation and looking at some more actions here. Wind loads. So we come to the variable action, wind loads. Now there are two ways of considering wind loads on the structure. For most bridges which span less than or equal to 40 meters, we assume static wind load on the structure. For very thin sections and very long span bridges, we do have to do a dynamic analysis considering the full time history type of an analysis, also known as the computational fluid dynamics. So let us see first how to apply a static load. The way Eurocode suggests the way to calculate the wind loads is that you have to first determine the velocity of the wind at a particular height. So we measure the height from the base of the structure, that is the foundation itself, from the ground you can say. So that's the height. We have the basic velocity of the wind at a certain height. Then we have to define the face area on which the wind load will be acting. So if the wind load is the leading action and other loads are all accompanying, then we consider the face area as the total height of the parapet plus the depth of the girder itself, and we add them up and multiply it with the length of the bridge, or just apply it along the length of the bridge as a UDL, and the direction will be horizontal axis direction, so it can be X or Y direction. If the wind load is an accompanying action, and say traffic load is the leading action, then we have to consider the total height of the vehicle as well as the height of the girder in order to consider the face area for the wind load calculation. And once we do that, we use this formula and apply the wind load as a UDL along the transverse direction. So it's fairly simple. Just like we applied permanent loads, we just have to calculate the UDL value in the X or Y direction. For aerodynamic effects of wind loads, which happens very quite commonly for long span bridges with very thin sections, Eurocode suggests, actually the Annex E and F of Eurocode suggests some methods for designing this type of, or checking for these type of sections. Basically, aerodynamics will lead to vortex shedding, which basically is generation of vortices on the leeward side of the deck as shown on this image. So alternate vortices will be generated, and this will lead to vibration of the bridge in a direction perpendicular to the direction of the wind. Then it can, there is also an effect called flutter. So if wind velocity is more than a critical velocity, which is also known as the flutter velocity, then it will lead to some instabilities of the thin plate sections, like as shown in this video animation here. That also needs to be checked. And also galloping, which is self-induced vibrations of the flexible structure, which as all of you might be aware of, the Tacoma Narrows Bridge, it was an example of the galloping effect that led to the failure of the bridge. Now, how to model these type of aerodynamic effects in a finite element model? So, because these are not normal static analysis, we need a detailed finite element analysis software. So here the animation that you're seeing is taken from Midas NFX, which is a multidisciplinary analysis package. So there are two ways of analyzing computational fluid dynamics. You do a 2D CFD analysis, which basically assumes the bridge deck as rigid, and the fluid is meshed, or the air is meshed around the deck profile. So this entire thing is a mesh, and then we apply different parameters for the boundaries and carry out the dynamic analysis. And then there is a 3D dynamic CFD analysis, which considers both structure and fluid as flexible. So you can model or see the deformation within the structure itself instead of considering it rigid. So we won't be going into very details of this because these are detailed analysis which require a much more time, which we can use to focus on some other actions. So thermal actions now. Thermal actions according to Eurocode have been distributed into these three types of you can say actions, including uniform temperature, which is a constant temperature applied on the section for expansion or contraction. Then you have linear variation of temperature, which is shown in the diagram. You can have linear variation of temperature along the vertical axis or along the transverse axis of a section. And then you have nonlinear temperature variation on a section, which leads to self-equilibrating stresses on the section itself. Now, how to consider these temperature values at different heights on a cross section? So for that purpose, Eurocode has divided each and every bridge into three categories. So you have a bridge consisting of steel deck, or a composite deck, or a concrete deck, and these are the different types of bridges. And for all of these three types, Eurocode has defined different temperature gradient or temperature difference to be considered. So we'll look at uniform temperature first. So uniform temperature, you first identify the initial temperature of the bridge. So T0 or T0 is the initial temperature of the bridge. Then the shade air temperature, which is the x-axis of this diagram, is calculated from the National Annex of Eurocode Part 5. Eurocode 1 Part 5, and based on this diagram and the type of the section which we discussed in the last slide, you can find out the final temperature of the bridge. So the final minus initial temperature of the bridge will give you the actual temperature required for the contraction or expansion of the bridge model. So the way we model uniform temperature in a finite element analysis software is through element temperature loads. So let's see in a model how to do that. So I'll just, in the same example, I'll undisplay the brush in the flow loads here. Okay, so we have the temperature option, element temperature. So you have to select the initial temperature. We can keep it as 0 because it's only the difference that matters between initial and final. You can set the initial temperature as some value and then enter the final temperature which you obtain from the diagram which I showed on the slide. And you can then apply it to different elements in the structure. So to the composite steel girders, or if you have any concrete deck, you can apply it on top of that. Then temperature difference, which is the nonlinear temperature. Temperature difference is has been defined in the Eurocode as a summation of linear and nonlinear temperature difference. So linear temperature is just simply defining the difference in the temperature between the top and the bottom fiber of a section. So it's very simple. We use a linear temperature gradient function in the finite element software to apply this temperature. Nonlinear temperature is a bit tricky because if the section is not like a uniform section, say if it's the width is varying at different height of the section, then you have to divide the section into equivalent rectangular strips. So Eurocode gives you such kind of temperature variation. So say between height 1 to height 2, you have a temperature variation. So between those heights, you need to convert the section into an equivalent strip and then apply the temperature to each strip individually on a particular section. So I'll just show you in the software how we can do it in the finite element analysis package. So for the linear temperature, we have got temperature gradient option here. So as you can see in the diagram, you just have to give T2 minus T1, which is the top minus the bottom, and just enter either let the software calculate the total height of the section, or you can enter your own height difference. So for example, for a composite steel girder, the Eurocode idealizes the temperature difference as the temperature applied only on the deck. So I'll take you back to the slide. So the normal procedure is this one for your composite steel girders, but Eurocode has a simplified approach where you can apply the temperature only on the small only on the deck thickness as a linear temperature difference. Now, for nonlinear temperature, we can use the beam section temperature option. So here you can define heights and temperatures at different levels. So for example, I just enter a few values. So I've divided my section previously into rectangular strips, and I can enter some elasticity values as per the material. So if it's a composite steel girder and I want to apply it on the deck, then I'll use concrete elasticity and concrete thermal coefficient. So Eurocode defines some coefficient for thermal expansion and contraction, which you can use. And that's the thickness, or sorry, the width of each strip between two heights. So for example, if I want to apply between top and say 0.1 meter from the top, so let's say the thickness is 2 meters, width is 2 meter for the section, and I'm measuring from the top. So I change the reference from the top, and this is a vertical temperature difference, so z-axis. And height 1, say that at the top the temperature difference is 20, so height 1 is 0 and height 2 is 0.1, and say at the top the temperature difference is 20 degrees, and at 0.1 meter below the top we have 10 degrees, for example. Add, and similarly we can add another distance, this time 0.1. We can change the width of the section between the next strip, and we can enter a new height level here, so 0.4, and from 10 to 4, for example, and add. So you can keep on adding several such variations as per the diagrams given in the Eurocode, and then we can apply them to different elements and carry out the temperature difference analysis and look at the different stresses or moments that are obtained due to the summation of uniform temperature and temperature difference. Now, having said that you have to divide the sections in rectangular strips, you may not need to divide it if your sections are already in the library of the software. So there are many sections for which you don't have to divide the strips, and a lot of sections are already there in the library of the software. So most of the cases we can directly apply the temperature gradient without having to worry about rectangular strip widths. Now moving on to earth pressure. So earth pressure is applied as per Eurocode 7, and the published document 6694 gives some special recommendations to the earth pressure loads. So the earth pressure loads consist of vertical surcharge due to any road traffic and permanent loads, strain ratcheting, which is the kind of fatigue in the soil due to thermal expansion and contraction of the abutments and including the deck. And to take care of this strain ratcheting phenomena, the PD document suggests some K star value, which is equivalent coefficient of earth pressure value for calculating horizontal earth pressure on the abutment. So this value is calculated based on the maximum possible thermal expansion or contraction to be assumed in the deck. And using that we calculate the K star value, and we apply the earth pressure as unit weight times K star times the height from the top of the abutment. So as shown in the diagram, it's applied like a triangular loading. So let's see how to apply this on the abutments in our example. So just open up the earth pressure model. So here we go. Here we have we have an abutment here which needs to be applied with earth pressure. So hydrostatic earth pressure option is used, hydrostatic pressure loads. We change the load case to say soil pressure or earth pressure, and according to the diagram we can see that that's the distribution it will have. we can calculate the top pressure and the bottom pressure based on the whatever vertical pressure we are getting or surcharge we are getting on the top. So we can type in the reference height, which is the top of the abutment. So this is the top of the abutment, and constant intensity at the top. So that's the horizontal pressure at the top. So let's say enter some value 5, and then the variation, this should be equal to gamma times K star. Gamma is the unit weight of soil, and times K star. So let me assume say 20 kilonewton per meter cube, and then you can select all the abutment elements and apply. So oops, sorry, that sign is reversed. We just have to put in -5 and -20 here, and we'll have the reverse direction. So that's how the earth pressure load is applied on the abutments by calculating the K star values from the PD 6694. Then we move on to actions during execution. So there are different types of actions we need to consider when the bridge is being constructed. So starting with some basic ones, which involves personnel and hand tools, which is applied as a UDL of 1 kilonewton per meter square on the entire on the constructed structure. And then we have wet concrete load, which is very crucial because in multi-span girder bridges, composite girder bridges, we may not be pouring the wet concrete at all the girders at the same time. We may be pouring it at different phases. So that needs to be considered in the construction stages, which we will see how to do it in the software. Movable machinery like your form travelers, those loads needs to be considered. So generally they are applied as a point load. As you can see in the image here, it's a balance cantilever construction, and you have a point load applied at the ends representing the moving machine or moving formwork. Let's see how to apply construction stage loads on the structure. So I'll open up the construction stage model. Okay, so here's an example of a composite steel girder bridge again. Now, I'll just quickly show you how the bridge is being constructed. We have made 3 construction stages. Say stage 1, which has got all the steel girders in. Stage 2, we have got the first span composite. Let me also display the supports so it will be clear where are the intermediate and the end supports. So that's how the supports are there, and stage 3 is the final stage where all the deck becomes composite with the steel girders. Now, how do we assume composite or execution loads on the bridge at different stages? So first of all, we create groups. We create groups for all the different loads we want in the construction stages. So there I've created different groups for wet concrete, construction loads on span 1, span 2, etc. And then when we are applying the loads, we just have to make sure, say element beam loads, we are applying wet concrete load. We have to make sure that we include them in the right group. So that's wet concrete load 1, for example, and apply it on a beam on the structure. So by beam, I mean in this case it will be a steel girder. So we just select them and apply on the structure. Now when we are defining the construction stages, say stage 1, I have to just make sure that I've included the loads in the correct stage. So for example, stage 1, I have wet concrete 1 poured because the concrete in the span 1 will be poured in construction stage 1. And I have some other loads like construction loads on span 1 on the first day of the construction stage. So they are all applied on first day. Then stage 2, you see I have deactivated or removed my construction loads from the span 1, which includes say personnel and hand tools and other types of loads which we don't need, say formwork for example. But I've applied some new loads now, which includes the wet concrete on span 2 and construction loads on span 2. And then on stage 3, I've applied the surfacing and other parapet loads for long-term effects, and then deactivated my other construction loads which I don't want in the final stage. And that's how we can consider different loads in different stages. So going back to the presentation, some other types of loads that are important when we are constructing the bridge include pre-stressing, or you can say post-tensioning in this case, internal post-tensioning, internal pre-tensioning, internal post-tensioning, or external post-tensioning. Sometimes post-tensioning is also done on the same section in multiple stages. So all those things need to be considered as actions during execution, and the corresponding load factor should be associated with it. Shrinkage and thermal actions, hydration effects of concrete, these can be considered in the analysis in the construction stage using the time-dependent effect. And wind actions, which are generally used for checking the stability of steel girders during construction. These can be applied as a UDL. And accidental actions, say if a precast segment falls on an existing structure, those type of actions can be simulated. Now I'll focus on the pre-stressing and shrinkage bit here. So I'll take you to another model and see how we can apply actions during execution, especially related to post-tensioning and other effects. So here we have again a bridge constructed in different stages. I'll display the tendon profiles for you. So that's the post-tension tendons. You can see this type of draped tendons, and just to show you how the bridge is being constructed, that's the box girder bridge, and it's being constructed span by span. That's one span, two span, and so on. Now to define tendon profiles, we have inbuilt wizards here for modeling the tendons. So you can define first the property of the tendon, which type of tendon you want, post-tension, pre-tension, or external, and tendon material can be selected, strand diameters, different types of strand diameters are here. Then relaxation coefficient, strength of the tendon, friction and anchorage losses can be defined. Then profile can be defined, either you can bring it from AutoCAD files, or you can just paste it from Excel, the different coordinates of the tendon, and consider them in the structure. But the real issue is how to consider them in different stages. So for that, we have tendon pre-stress option. So what we do is we select some of the tendon profiles. We have already generated some load group names, which are displayed here. We select some of the tendon profiles and give some jacking force, either as a stress or as a force, some values here, begin or end, depending on which side or which end you want to pre-stress. And then grouting, how if it's a bonded tendon, after how many stages you want to grout the tendon. So all this information can be entered. And then finally, when you are modeling the construction stages, you just have to make sure that you have the post-tension tendons in the correct stage. So like I have CS1, stage 1, with pre-stress 1 group, then pre-stress 1B and 2B, and so on. I can include my other tendon load groups in different construction stages to consider the pre-stress. Tendons are considered as loads in the structure, so that's why you have load groups to define your tendon pre-stress loads. Now, in terms of creep and shrinkage and other time-dependent behavior, the finite element software provides for detailed long-term, short-term and long-term analysis directly from the code. So you can select creep and shrinkage, select the different standards you want to go for, strength of concrete, and then it will draw a graph for creep and shrinkage strain, coefficient and strain respectively. And that will be considered as the construction stage progresses. The age of concrete will increase and you will have the shrinkage and creep considered accordingly. Then compressive strength gain. So concrete will gain its strength as you gradually increase the number of days. That can also be considered. So all the hydration effects of concrete, the early shrinkage and also the later on long-term creep and shrinkage are actually part of the actions during execution, and they should be considered correctly in the software when you are doing the construction stage analysis, be it any type of composite steel or concrete post-tension bridge. Okay, now I'll move on to the traffic loads option. So first, focusing on the road bridges, we have different load models for traffic loads, including vertical load models from load model 1 to 4, and horizontal forces, fatigue verification models, and actions for footway loads on road bridges. Then also we have actions for accidental design situations like vehicle colliding with the parapets or an accidental load, for example. Let's see what kind of traffic actions we're talking about. So first, for any traffic analysis, traffic load analysis, we have to define the lanes on the structure, on the bridge. What is the carriageway and what are the remaining area and footway lanes? Those things need to be defined. So there are three types of model when we are looking at bridges. One is a line beam model, one is a village model, and one is the finite element shell model. If it's a line beam model, traffic line lengths can be directly applied on the line element, and if there is any eccentricity with the line element, that will be considered as a torsion. So you can see on the screen here, if you have a load here and you have applied the loads on this line element only, then it will be applied as a vertical and as a torsion load on the line beam. If it's a grillage model, then we distribute the loads via cross beams. So we have cross beams here. So if the load is placed somewhere here, it will be distributed first to the cross beams and then via the cross beams to the main girders. So that's how the distribution takes place in line beam and grillage model. For finite element shell models, we have traffic surface lanes with which apply the lane loads directly on the slab area, and so you need not define any type of cross beams or any distribution pattern. It will automatically be distributed based on the plate mesh. So these are different carriageway types, and Eurocode defines some rules of how many lanes should be there, how many notional lanes should be there based on the carriageway type and the width of the carriageway. So let's see what kind of loads we are talking about. Load model 1, which is applicable for all types of bridges. It's the most common type of load, most expected type of load on the bridge. It consists of axle loads and tandem loads, axle loads and UDL. And you have different adjustment factors to be applied as per the National Annex. So these values which you are seeing on the screen are as per UK National Annex. Also psi factors for load combinations are also taken from the UK National Annex. Load model 2, single axle load. This is used for verifying only short structural members, most commonly in case of orthotropic slabs is used. So it's a heavy load applied on a very short structural member. Load model 3, these are special convoys, multi-axle truck loads which can straddle transversely between lanes. So this is defined in the Eurocode National Annex, UK National Annex, special vehicles and special ordered vehicles. And they have a different wheel spacing as well. A number of wheels can be different. Dynamic amplification factor needs to be applied to all those vehicles which have a speed less than up to 70 kilometers per hour. So this is a list of dynamic amplification factors as per Eurocode. And finally, load model 4 for crowd loading applied on the entire bridge as 5 kilonewton per meter square. Let's see how to apply these loads on the bridge. Right, so this is a grillage model, and I have already created a group called cross beams, which consists of all my transverse members, because these are the members through which the loads will be transferred. Then moving load option, traffic line lanes. I define the lanes, add, say, lane 1, give a name to it. You can give any name. The software will decide whether it is notional lane 1 or notional lane 2 or and so on. So say there's one lane and define an eccentricity from a reference line, and then wheel spacing, lane width. If you have a skew on the bridge, you can define the skew angles and then mark the start and end points to create the lane on the bridge. So just to display the lanes which I've already generated here. Okay, so you have footway lanes, remaining area, lane 1, lane 2, and then remaining area and footway on the other side. And the loads that we need to apply can be applied from the vehicles, standard vehicles, road bridge, load model 1, 2, 3, 4, So here you can adjust your adjustment factors, enter the psi factor as per National Annex. And load model 3 UK National Annex, you can define your SV80, SOV 250 and other special vehicles. And if there is a footway on the bridge, you can define the footway loading on the bridge. Any kind of user-defined vehicle, like user-defined load model 3, or any kind of abnormal vehicle can be defined using these options here. So now let's look at once we define the vehicles, how do we combine these vehicles? How do we make groups of combinations out of them? Okay, these are some horizontal forces here, just to give you an idea. So horizontal forces, braking and acceleration depend on the loaded length and also the weight of the vehicles. So in terms of, if you compare railway bridges and road bridges, railway bridges the effect of braking and acceleration forces and centrifugal forces will be much higher as compared to the road bridges because of the heavier loads and because of longer length of the longer loaded length. Groups of traffic loads. There are 6 groups which the Eurocode National Annex for UK National Annex suggests. You have Group 1A, which is load model 1 and Footway. Footway, you apply it with a reduced value. And then load model 2, Group 1B, Group 2, which is load model 1 and braking and centrifugal. Group 3, you have the characteristic values applied for the footway. And then Group 4, crowd loading, and finally Group 5, which is for special load vehicles and special vehicles in conjunction with the normal vehicles load model 1. So let's see how to create these groups in the software. So we go to moving load cases, add, and we select, say, Group 1A, load model 1, and since characteristic value needs to be used, so we ignore the psi factor here, and we use the reduced value for footway, 0.6 footway, 0.6 times footway. Include all the lanes that we want to be loaded, footway lanes in footway lane category, remaining area in remaining area category. So that's how we apply the Group 1A combination. For load model 1 and 3, straddling vehicle, we can consider load model 1, lane 1 and lane 2 as the selected lanes, and remaining area in the remaining area category. And then we can mention to the software that these 2 lanes are the lanes between which our vehicles will straddle. So that's how the software will automatically adjust between these 2 lanes and place the vehicle to obtain the worst effect between these 2 lanes. Psi factors should be considered for this case because this is a Group 5 case, because frequent value of load model 1 will be used. So like this, we can create several other combinations within our model. And what happens after the analysis is that we can look at the vehicle position for the worst case effect. So if it's Group 5, we can select one of the elements for maximum sagging effect and click apply. And just to clear up the view, I'll just undisplay all the lanes and remove the load values. So you can have a look. This red dots represent the axle loads, the special vehicle, and you have a 5 meter spacing between the load model 1 and the special vehicles as per UK National Annex. You will also notice that for maximum bending moment at this span, the entire bridge is not loaded, only half of the bridge or one span is loaded. So it loads only the unfavorable parts of the bridge, which is in accordance with the Eurocode. So that's based on the influence line analysis. So this is the type of combination I'm talking about. This is the figure taken from Eurocode National Annex, and you can look at these spacings are all considered by the auto loading option in the finite element software. Fatigue load models, most commonly fatigue load model 3 is used for most types of fatigue checks. And when you're using fatigue load model 3, we should not be combined with other load effects. So only fatigue load models should be checked for fatigue verification of the structure. Then we move on to accidental traffic actions. So these are nothing but some abnormal loading. For example, load model 1 axle can accidentally go into the footway loading, and you can consider a 200 kilonewton load on the footway for considering the accidental effects. sometimes vehicles can be collisions with the curbs or vehicle restraint systems or parapets. So Eurocode has given us a table of what kind of force needs to be applied transversely and vertically on the curbs and other structural components, so that we can consider these accidental effects. So these are nothing but point loads applied in different directions as shown in the table. It's fairly simple to apply as a static load. Traffic loads on railway bridges now. Railway bridges consist of, again, same vertical load models, horizontal forces, but here the horizontal forces are crucial, especially in case of curved railway bridges. So we will see how to apply centrifugal forces and combine them with the load models 71 or SW models for vertical effects. And track bridge interaction for the interaction between rails and the deck, and also dynamic analysis of high-speed trains. So the vertical load models for railway bridges consist of load model 71 and SW0, which are the which comprise of the normal rail traffic consisting of passenger and heavy freight. Speed of these vehicles are less than 200 kilometers an hour. So the dynamic effects are not considered through a dynamic analysis, rather they are amplified using a factor suggested by the code. Sometimes these loads may not be applied symmetrically on the rails, so there can be some eccentricity. So as shown in the figure, the center of gravity may not exactly coincide with the center of the track. So those eccentricity needs to be considered. Then some other vehicles include unloaded trains. Unloaded trains are specially used for wind load analysis because in these cases, since the vehicle is light, so wind will be the leading action, and we can consider the wind load factors accordingly. And then we have high-speed load model, which is used for trains greater than 200 kilometer speeds, and dynamic analysis is needed for this type of load models. So dynamic factor is calculated and applied for load model 71 and SW0. We should be cautious here that dynamic factors from Eurocode should not be applied to real train models. They should only be applied to load model 71 and Eurocode load models. For dynamic load and amplification factor or dynamic factor, we need the determinant length for each type of element, and that is, there's a table in Eurocode which lists out what length we need for cross beams, what length we need for main girders. So let's see in the software how we can do this type of rail mod analysis. So I'll open up a model. Due to lack of time, I'll be answering all the questions at the end of the presentation. So if you have any questions, you can type it in the questions window, and I'll handle them in the end of the presentation. So that's a curved, horizontally curved bridge. The lanes were modeled in the same way. That's line beam models. So lanes were modeled in the same way. There are two tracks. Then we have vehicles. So I'll go back to vehicles here. And we have load model 71, you see at standard. So we have railway bridge, rail traffic loads. And load model 71, we can consider eccentricity of lateral displacement of vertical loads, which I was mentioning earlier. You can enter the values here. Adjustment factors, alpha value as per National Annex. Normally it's 1.33, and some other vehicles can be defined. Then for all these types of rail models, for load model 71 SW0, we can apply the railway dynamic factor. So railway dynamic factor depends on the track maintenance quality. So Eurocode gives you two different formulas for these two types of track maintenance. You can select one of them and apply, and you can also define it as a user input. So instead of using the Eurocode calculations, you can just apply a dynamic factor from your own side. Once you apply this, you will have a table where you can then manipulate. So let's say if it's a grillage model, then you can assign some different dynamic factor or determinant length to cross beams, or different determinant length to the longitudinal beams. So in that way, the software will automatically consider dynamic factor differently for different parts of the model. Now, I was talking about combining vertical effects with centrifugal forces. This is an example where we need to see the centrifugal forces and combine them with the vertical loads. So that comes under the results moving tracer option in the software. So say I'm looking for beam forces here, let's say a maximum moment in this span, for example, and I click apply. So I've got the load distribution of load model 71. You see this is an asymmetric type of distribution because of the eccentricity which I defined on the track. So these two axle loads are not same. And now if I want to consider the centrifugal force with this vertical force, I can just click here, and there is a centrifugal force option where I can put in height of centrifugal force from running surface. So according to Eurocode, it's 1.8 meters. Maximum speed, I can enter the speed of the train, and radius of curvature, 500 meters for example, and click OK. This will give me a text file. I can extract such load effects for different locations on the bridge, and then I can simply paste it in the software command file here, and you can look at the effect. So that's the centrifugal force. You can see it is being applied in the perpendicular direction to the bridge. So that's how you combine centrifugal forces with the vertical forces. You can use this load case for your load combinations and for further checking the analysis results. So centrifugal forces, as I said, they are a factor of velocity and the load applied, and braking and traction forces can be applied on along the loaded length as a UDL. So braking or traction force, just apply it as a UDL along the direction of the bridge, and we have seen how to apply the UDLs for the other loads. So I won't repeat the process here. Now, track bridge interaction, we can assume or simulate the nonlinear interaction between the rail and the deck because of the ballast. So the ballast can be given with a nonlinear stiffness, so a different stiffness under unloaded situation and a different stiffness when the train is actually moving on the rails. So such kind of track bridge interaction can be done using the wizards which we have in the finite element Midas civil software. Let me just quickly open an example here. So that's just the base model, has materials and sections, and now I'll use the wizard. So that's the rail track analysis model wizard, and I'll open an existing wizard file. So you can do a parametric study. Say we have 10 spans, 40 meters each, and the span type is fixed free everywhere, and then rail section has been defined. So that's a typical rail section. Sorry, it's the material section is here. Yep. So that's the typical deck and a box girder, and that's the rail section. You can specify the spacing between the two tracks and the distance for the ballast. Then boundary condition, this is very crucial, and most important thing about the rail track analysis is the modeling of the ballast. So the track bridge interaction is actually done as per the UIC code specifications. So even Eurocode suggests the vehicles, the load models as per the with reference to the UIC code. So you can enter the different unloaded condition and loaded condition maximum yield values of your ballast, and the software will consider them for generating the springs. Then loads to be applied, so acceleration vertical loads to be applied on this train, and the direction of the movement of the train from left to right or right to left. And you can then generate the model. So you can click OK and generate the model files. That's the typical model generated. And if I display the links here, you will find that that's how the connectivity is in the finite element software. So you have ballast modeled as V-shaped links, and you have rigid links connecting to the bearing points. So these are your bearing locations on the bridge. And you can carry out the analysis for temperature. Temperature load is applied on the structure, and you have braking loads applied. So your braking loads are applied. The embankment is also modeled, and finally vertical train loads are also modeled on the structure. So you can do the analysis considering combined temperature, braking, acceleration, and vertical loads. So rail track analysis wizard is very useful for doing a track bridge interaction, and it models the ballast conditions in the nonlinear properties of the ballast conditions automatically. Then dynamic analysis of high-speed trains. So wherever you have speeds greater than 200 kilometers per hour, it's recommended to check the natural frequency of the bridge, and based on the natural frequency of the bridge, the Eurocode suggests whether you need to do a dynamic analysis or not. So dynamic analysis, if required, has to be done using a time history analysis. So it will give you peak acceleration versus time plots. You can check the maximum deflection for passenger comfort, and also whether the loads exceed the normal traffic loads of load model 71 or SW0. So this video will shows you how the train moves and how with each time step the deflection occurs on the bridge. Then train structure interaction. So this is used for complete nonlinear dynamic analysis, considering even damping and mass in the train carriage itself. So the train cars will be modeled as instead of modeling them as loads, we can model them as actual train cars with mass and some damping parameters. So this is animation from the Midas NFX software. You can do this type of nonlinear analysis. So there is a contact nonlinear behavior between the axles and the track, and between the track and the deck. So it's a complete train structure interaction, and you get this type of acceleration versus time response, which you can compare with the code. And then coming to the last few topics for today's webinar, dynamic analysis of footbridges. Eurocode 1 suggests that for footbridges, if the frequency of the footbridges are exceeding or within certain criteria, we need to do a dynamic analysis for footbridges under jogging, walking, and crowd loading. So the way we do it is we perform free vibration analysis, then apply forcing functions on the structure based on Eurocode, and then check for the acceleration time response. So this is as the image shows, this is the Millennium Bridge, and dynamic analysis was important for this bridge. If the vibrations in the vertical directions have a frequency less than 5 Hz, then we need to do dynamic analysis, dynamic moving load analysis on the structure. And for lateral vibrations or torsional vibration, it is 2.5 Hz. If it's within that, then we need to do a lateral vibration check as well. So let's just quickly look at a simple model, how the footbridge vibration loads are applied. Okay, that's a composite steel girder bridge. This particular bridge, we have already demonstrated the modeling procedure earlier. We'll just look at the different steps briefly. So first of all, we carry out a vibration analysis, pre-vibration analysis with mass and stiffness, and we get the vibration mode shape. So that's the mode shape. So that's the vertical mode of vibration. You see the natural period here is 0.55 seconds, or in Hz we can display it here. So for first mode is 1.79 Hz. So it's way below 5 Hz limit. That means we need to do a detailed check for the detailed time history analysis for the pedestrian actually walking on the bridge. Now from Eurocode, we can from the National Annex, we can take or define forcing function for walking. So that's the typical sign function for the walking loads and for the crowd loads as well. So crowd loads are usually having a continuous type of function because the whole bridge is loaded at the same time. And then we apply these functions at different points on the structure. So if I'll display the points here, so these are the different locations where they have been applied. Now they are applied in such a way that the difference between these 2 points and multiplied by the time required from moving from point A to point B, that should be in such a way that it should maintain a constant velocity as per Eurocode. So Eurocode suggests a velocity for the walking and jogging. So this velocity should be maintained. So the time difference of the pedestrian to reach from point A to point B should be decided based on the speed of the pedestrian. So we have got dynamic nodal loads. So you define the arrival time at point 1, point 2, point 3 based on the speed of the pedestrians. And once you have done that, we can, after carrying out the time history analysis, we can look at the time history graph for walking or jogging, for example, and plot it against time. And it will give us a graph resonance response like this. So you have peak acceleration. Here you can compare these values, the y-axis values, with the code limits and decide whether the bridge is safe for human-induced vibrations or not. So that's how we do the Eurocode dynamic load models, apply the dynamic load models in the footbridges. So they are nothing but sine functions defined from Eurocode and applied into the structure, into the model. So just a capture of the same thing. And the vibrations, animations can be extracted from the software for the worst case mode. The final type of action is the accidental action. So accidental actions are impact or collision, which is basically a dynamic force applied for a very short duration. There are 2 types of impacts that need to be that we can assume for simulating accidental actions. One is hard impact, where the energy is dissipated by the impacting body. So the structure remains rigid, and the impact is assumed as a point load, as shown in the figure. That is more or less a quasi-static analysis. So impact is assumed as a point load. These definitions are there in the Eurocode, so you can find out the values for these. So this is vehicle or collision on structural components. This is a ship collision on bridge piers. So this is hard impact idealization. Soft impact means the structure itself is treated as flexible and it absorbs the impact energy by elastoplastic deformations, which means that we need to have some sort of a nonlinear material behavior for the material of the pier or material of the abutment or whichever component we want to analyze. So that should be defined first. And Eurocode does give this type of elastoplastic material models in the annex for the accidental actions. So let's see how to analyze for soft impact. Hard impact is very simple. We just apply point loads. So it's fairly similar to what we have seen in the accidental actions during traffic loads. So nonlinear dynamic impact analysis needs to be carried out for these type of cases. We need to define the material property, the nonlinear material for the pier itself. And again, this is a snapshot of our detailed analysis model software called Midas NFX. So for each short time interval, we can analyze and see the deformation occurring in both the bodies. So both the impacted bodies as well as the impacting body. So we can look at the stress distribution and how the pier is deforming, and similarly vessel collision, ship collision with the piers from different angles. See, this is a typical type graph for a material for the nonlinear behavior defined in the Eurocode, which can be considered for nonlinear impact analysis. So this is a very high-end dynamic impact analysis which uses an explicit solver. So it's not a simple type of analysis. It needs modeling time is quite extensive, and the results are less conservative compared to the hard impact. To end this presentation, load combinations, Eurocode 1 National Annex for UK suggests some psi factor values for our bridge variable loads. So you have different psi factors for groups of combinations, and the total the gamma factors for the overall combination for permanent variable actions for set B and set C can be considered. To consider the load combinations within the software, we can use the load combinations tool. So that's the same the road bridge here, and we can include results, load combinations, say steel design if you want to do steel design. So Eurocode suggests different load factors for even the permanent loads. So for example, your wet concrete load should have a different factor compared to your self-weight of the steel. So here you can see that I have separated out my construction stage loads into two categories, dead load and erection load. So what you can do in the analysis software is that you can separate out all the construction stage loads which are to be assigned with different load factors from the existing load cases. For example, I haven't included wet concrete in this list because wet concrete will be applied with 1.35 and steel will be applied with 1.20. So all the other loads I have not included here. So whichever I want to apply with different factors, I include under the distinguished load cases and then apply them with different factors here. So dead loads, erection loads, creep loads. Shrinkage is generally applied with a factor 1. So applied with a factor 1. Now Eurocode combinations can also be auto-generated from the software, but they need to be manually checked as well because some of the national annexes may not be automatically reflected because these are all the recommended Eurocode values. So for example, I selected 1.35 for permanent loads, and road traffic, say GR1A is a frequent, sorry, GR5 is the frequent combination. Okay, and click OK. So it automatically generates all the strength and serviceability combinations. Okay, and you can look at the factors here and see the results for the combination. So that's the end of this presentation. I hope you liked the presentation, and if you have any questions, you can type in the questions window or mail us at uksupport@midususer.com. I know we have exceeded time trying to cover all the different types of actions, and apologize for that. If you have any questions, as I said, or you need any bespoke demonstration at your offices, please contact the Midas UK support team, and you can mail or either call this number. And we do have a YouTube channel. You can search on YouTube, type Midas UK, and you will have a list of all the past webinars that we conducted. This webinar will be also uploaded on YouTube shortly after we have finished converting the video, and then you can have access to we'll send you the video link so you can have access to it. And thank you for listening to this webinar, and see you next time. Thank you.